Welcome all of you. So we'll wait for a few more minutes to join some other peoples, and then we'll start our session. Okay, we'll start our today's session. So we are here to discuss some of the problems based on the course titled "A Study Guide in the Organic Retrosynthesis, a Problem Solving Approach." So in this course, we are dealing with the some topics on the week three covered by the professor. And before going to the discuss the problem that I have taken, so does anyone have any doubt regarding the any regarding this course, or if you want to discuss any question, you can ask me right now. So this session is open for any questions if you have any. And also, I have shared in the chat box one drive link which contain many uh, books in the form of PDF. So you can use that link. So you can get. It contains most of the reference book PDF. So like Clayden, McMurray, Pinar, as well as the Carithor, Nance. So many reference books in the form of PDFs are there in that drive. So you can have a look at that also. So we'll move to the some of the problems. So if you don't have any doubt, or you can stop in between to discuss any doubt if you have. Okay, so today here I'm going to discuss the chemoselectivity and some part of the radioselectivity as well as the I will not discuss today at least in this video regarding the stereoselectivity, but we will deal with the we'll discuss stereo selectivity. Sorry, latter part of this our course. But right now we'll focus on the chemoselectivity, and also I will discuss some of the concepts so you can able to solve the questions given in the assignment. So basically there are three main types of selectivity. So the first one is the chemoselectivity. So basically, this chemoselectivity generally deals with the which functional group will react. Then there is radioselectivity, so where it will react. So you can keep in mind these short form for or short definitions for these concepts. And the stereoselectivity is the how it will react in terms of the stereochemistry of the product. So these are the three type of selectivity: the chemoselectivity, that is which functional group; radioselectivity, where it will react; and the stereoselectivity will be how it will react. So we'll discuss some of the problems on the chemoselectivity. So basically, it is deals with the preferential selectivity of one functional group over other. And if you have more than two different functional group, two or two more than two different functional group with unequal reactivity, then this concept come regarding the chemoselectivity. So if you take the example, so in this one you can see it has the this compound which has the phenol OH functional group and the NH2 functional group. So if you add the excess of the acetic anhydride and at 100 degrees Celsius in toluene and reflux it, so what we will get? We get the acetal protection on both sides. So OA, oxygen also get protected and the nitrogen also get protected using by the acetal group. And so if you want to do this selectively, so if you look at the structure of paracetamol, in the structure of paracetamol, only amine functional group is protected by acetyl. And if you want to prepare this paracetamol, then how we are gonna deal with this type of chemistry? So then what we can do, we can add selectively one equivalent of the acetic anhydride and catalytic amount of pyridine. So if you look at the reactivity of this OH and the NH2, this NH2 is more electron rich compared to the OH group, and therefore what happens? This measure we get this product which contain the nitrogen has the acetyl group attached, and we get the our desired product paracetamol. Or else what we can do? So we do the reaction that we have discussed first. So do the excess acetic anhydride, so we get 100% of this product. And then what we can do, if we add the NaOH, so this NaOH selectively deprotect this ester, and this is the ester functional group, right? So this selectively deprotect the. So if you look at here, so in this case, this is the ester functional group, right? And the other is this is the amide functional group. So if you add the NaOH, this NaOH chemoselectively hydrolyze the only ester and unaffect the amide functional group, and we get the selectively paracetamol as a product. So this is the use of the chemoselective reactions in the day-to-day life of the organic chemist. And if you look at the another example, so here there is one example. So here you can see if we have the hydroxy as well as the secondary amine, and we add the benzyl chloride, and in presence of the acid, so what happen? In presence of acid, this amine get protonated. So in presence of acid, so what happens? This amine get protonated, and this will be no longer available for electron donation or the attack on the nucleophilic attack on this carbonyl center of methyl chloride, sorry, benzyl chloride, and we get the selectively this O protected compound. So the reaction occurs at the oxygen center and doesn't occur at the uh, amine center, nitrogen center. But if you do the reaction in the presence of triethylamine, what happen? Then this nitrogen in the basic condition is more reactive compared to the hydroxy group, and we get the selectively this N protected compound. So just by varying the condition, like here acidic condition and here basic condition, we get the different selectivity. So this selectivity is basically either reactivity difference between the functional group or the reactivity uh, difference in the reaction condition or the reagent. Then we look at the some other example like ketone ester reactivity between the carbonyl compounds. So let's say if we have the this C triple bond C negative and Li positive, right? So this is the this carbon has the negatively charged, and if you look at the carbonyl center, so this is now in the starting material there are two different carbonyl center. One is the ketone and one is the ester. And if you look at the reactivity, so the ketones are more reactive toward the electrophile than the ester. Why? Because if you look at the ester, which has the this O group, so which has the lone pair, this hydroxy group, sorry, this oxygen, and it can involve in the conjugation. So this center ester, the carbon center of the ester is not that much electropositive compared to the ketone, and the ketone is more reactive or toward the electrophile than the ester. Therefore, the reaction selectively occur if you add the selective one equivalent of this uh, reagent. So we get this product majorly. And if you look at the reactivity order of this carbonyl compound, so the aldehydes are more reactive than the ketones, and then the esters, amides, and the carboxylate anion. So you can keep in mind this reactivity order for these different carbonyl compounds, so which will help you to solve many problems, maybe in the competitive exam or also in this course also. Then, if you look at the reduction of this chemoselective reduction, so I will not tell you where these concepts gonna useful for your solving the assignment problem. So you have to correlate the concept from whatever I am talking right now, and where you can apply the same concept on solving your assignment question, right? So this is the another chemoselective reduction reaction. So if you look at the this reaction, so this is the starting material which has the ester. Then here there is amide, not sorry, not amide, because if you look at here, there is one more carbon, and then this is the carbonyl. So this is basically a ketone, and this is acid, sorry, the ester. See, and if you add the NaBH4, so this NaBH4 is mild reducing agent. It only reduces the ketones, not and giving unaffected the ester. So it will give the selectively reduction of this ketone over the ester. So this is what you get in the product. So which has the only ketone is get reduced, right? And ester group will remain unaffected. Then the another example here. So let's say if we have the alpha beta unsaturated carbonyl compound and we do the H2PD reduction, so it will selectively reduce the double bond and keep unaffected this carbonyl compound. But if we use the NaBH4 in the cerium trichloride, this cerium salt, then what happen? It will selectively reduce the carbonyl compound and keep unaffected this olefin. So this is how you can perform the reaction. If you want to selectively reduce the olefin, then use this condition. And if you want to reduce selectively ketone of the alpha beta unsaturated compound, then you can simply use the this NaBH4 and in place of CeCl3 salt. So what is this? This is the it has the name reaction. So if you just recall that name reaction, that will be nice. Or also I will discuss this name reaction later part of this video. Then if you have the another starting material which has the ketone and alpha beta unsaturated carbonyl group, and so this is the two different condition. So if you use the BH3 in 1 by 3 equivalent of the starting material, then what happen? It will selectively reduce the alpha beta unsaturated compound, carbonyl compound, and it unaffect this ketone, isolated ketone. But if you use the NaBH4, and in case of NaBH4, what happen? It will selectively reduce the isolated ketone and keep unaffected alpha beta unsaturated ketone compound. So you can keep remember these two reagents also. So okay, then we'll move to the next question, next concepts. All right. So if you have now the chemoselective reduction of the alkenes or alkyl ketone, that is the alpha beta unsaturated ketones. So this is another reagent combination we can use. So it will selectively reduce the isolated olefin. So earlier we have seen how to reduce isolated ketone. Now in this case, uh, we are focusing on if you have these two type of olefins. One is the one olefin is in conjugation with the ketone group, and one is the isolated olefin. Then how to reduce selectively this isolated olefin? So if you want to reduce this isolated olefin, what we can do? This PPH3 thrice RHCl salt. If you use this reagent in and the hydrogen in ethanol solvent, then we can selectively reduce this isolated olefin. But if you want to use this conjugated olefin conjugated with the carbonyl compound, then what we can do? We can use the K select right in the THF, or also there is another condition like Me in copper, MeCu, and diabal H. So these reagent combinations we can use to reduce selectively this conjugated olefin part. The another chemoselective reduction of this ester or cyanide group. So this calcium borohydride we can use. So it will selectively reduce the ester and keep unaffected the cyanide group. So this has you can also have a look at this reagent. So this is very similar to the NaBH4 and all reducing reagents compared not strong enough to ally BH4, but stronger than the NaBH4. So another chemoselective reduction of this alkyne or alkene. So okay, so we have the alkene and the alkyne, and if you want to selectively reduce this alkyne, that is the triple bond, then what we can use? We can do the palladium in calcium carbonate. So and quinoline as a ligand. So in this condition, we can stop selectively the reaction at the olefin stage. And also there is one more uh, regarding the stereochemistry stereoselective reaction here occurs. So if you do the reduction by this manner, and if you have this type of alkyne, so this gives this Z, that is Z olefin as a major product, not the uh, E. So if you have the olefin in this manner, so we call it as a Z, right? And if you have the in this manner, we call it as a E or Z, or in bracket we can call it as a cis. And this as a trans, right? So if you want in this reagent condition, we can selectively get the Z olefin as a product. Now my question is, if you want now the E olefin, that is the trans olefin, what reagent condition you will gonna use? So here you get the Z olefin, that is the cis. But if you want trans type olefin, then what condition you can use? So if you use these condition like lithium in NH3, in that case, you can get the selectively E or the trans alkene as a major product. So in this condition, you get the this type of trans alkene as a major product. So whenever you do the reduction of the alkyne using the hydrogen and the palladium catalyst, so you get the cis addition of these two hydrogens. But if you use the lithium or sodium in the liquid ammonia, so basically this goes by a radical pathway. So radical pathway get followed in this reduction reaction, and we get the trans alkene as a major product in this one. So this is one example of sorry, the stereoselective reaction you can keep in mind. So we'll discuss this again later also. But for now, when we are discussing such questions, so that's why I just discuss here. Okay. So the another type of reduction is the chemoselective reduction of these carbonyl compounds. So that we have already seen one of the example. So here we have the ketone and the ester. So it will selectively reduce the ketone group and keep unaffected the ester. The another example is Clemenson reduction. So this carbonyl group will convert into the this type of group. So this is the Clemenson reduction reaction. So you can selectively reduce the carbonyl to the alkane type of system. So this entire carbonyl group is getting removed. So this entire group is getting removed, and we get the this product with the two hydrogens at the centers. And do you know what is the reagent condition for the Clemenson reduction? So there are two different type of reduction for such carbonyl to the alkene. One is the Clemenson reduction, and another one is the Wolff-Kishner reduction. So you just do some homework. So what is the reagent condition for the Clemenson reduction, and what is the reagent condition for the Wolff-Kishner reduction? So this is question for you. Okay. Then another here, alpha beta unsaturated ester in presence of alkene. So this is the alpha beta unsaturated ester, and we have the alkene. So if you add the magnesium in the methanol, so it will selectively reduce the alpha beta unsaturated olefin and remain unaffected this isolated olefin. So this isolated olefin will be remain unaffected. The another question here, another problem here is the chemoselective reduction of amides in presence of ester. So you have the ester and amides. So if you add the BH3THF, so it will selectively reduce this amide, and we get the amine as a product. And the ester group will remain unaffected. So you can see ester is remain unaffected, but this amide here we got the two hydrogens now. So we did the reduction of these amides chemoselectively. Does anyone have any doubt up to here? We can stop and discuss that one. Okay, if you don't have doubt, I will move to the further. So this is just a summary slide for the chemoselective reduction and the this hydride based reagent. So let's say we have the imine, aldehyde, Then the ketone, this is the ester, this is amide, and this is the carboxylate anion. And we are going to look at the reactivity range of this different hydride based reagent. So this is the H2 and palladium catalyzed reaction. So it generally reduce the imines and at some reactive aldehydes also. Then in a sodium cyanoborohydride, it will selectively reduce the imines and aldehydes, but not all aldehydes. So this is dot means if the aldehyde is reactive, then only it will reduce, otherwise it will not. Then if you look at the NABH4, the NABH4 reduce the imines, aldehydes as well as the ketones, but doesn't react with the ester or amides or carboxylate anion. Then if you have the LiBH4, so this lithium borohydride reduce the aldehydes as well as the imines, aldehydes, ketones, and this LiBH4 also reduce the esters. And if you have the lithium aluminum hydride, LiAlH4, so this LiAlH4 reduce all except carbonate anion. Also, it show the reduction of this carbonate anion or the acids as well, but the reactivity is lower, so we get the lower yield in most of cases. But if you add the BH3, then it can reduce the some esters and amides and acids are more reactive toward this BH3. So if you want to reduce the acid as well as the amides, we can use the BH3 in the THF or the diethyl ether. So this is just a summary slide. You can uh, keep noted this slide, so it will help you to solve many problems, many questions. Okay, so I'll move to the further part on the oxidation. Whatever we have seen here up to reductions, but there are some oxidation, chemoselective selective oxidation reactions. So let's say if you have these starting material which has the two different type of hydroxy group. So one hydroxy group and another, this is the secondary hydroxy, this is the primary hydroxy group. And if you do the Ag silver carbonate and the silite in presence of the benzene solvent, we can selectively oxidize this secondary hydroxide group and remain unaffected this primary hydroxide group. Then second reagent is the NaOCl in acetic acid and water at 25 degrees Celsius, that is the room temperature. So it will selectively reduce the secondary and remain unaffected this primary hydroxy group. Another selective oxidation reactions are here. So in this case, you can have a look. This alpha beta hydroxy group and this is normal hydroxy group. So if you add the MnO2 in the chloroform, it will selectively oxidize this alpha beta unsaturated hydroxy group. So here there is double bond. So this double bond assists in the oxidation reaction by using this MnO2 catalyst. Then another oxidations. So if you have such compound which has the lactols, basically this is the the oxygen involved in the ring formation here. And if you use the Ag uh, AgCO3 and the silite, so it will selectively oxidize this hydroxy group and remain unaffected this another hydroxy group which is not in the vicinity of this lactol. Then there is another two different type of now here it is the this whatever we have seen normal oxidation reaction. Now here there are epoxidation reaction, chemoselective epoxidation reaction. So let's say if we have the alpha beta unsaturated olefin, the carbonyl compound, and we add the potassium hydroxide and H2O2. So what it will do? It will selectively do the epoxidation on the olefin which is in conjunction with this carbonyl group. So you can see. So here epoxidation occurs and this olefin, this double bond remain unaffected. Now if you want to do epoxidation on this carbonyl, then what we can use? We can use the metachloroperbenzoic acid in DCM solvent. So it will selectively do the epoxidation on these isolated double bond or isolated olefin. So this concept we can use for solving one of the problems in the assignment. Okay, any doubt in this question? We'll move to the next question. So here, this already we have discussed earlier, the chemoselective acylation. So if you add the one equivalent, then it will only do the acetylation on the nitrogen center, not on the hydroxy center. Here another question is chemoselective alkylation of phenols over carboxylic acid. So let's say we have the carboxylic acid and the phenol, and in place of base, it will form carbonate anion. Then also this O will be the negative charge because this proton is also the acidic proton. Then this O negative can attack on the alkyl iodide, so it will give the selectively the alkylation occurs on the phenol center selectively. Here now it's all about whatever we have discussed about the chemoselectivity. We'll see some problems on the regioselectivity also. So let's say we have, so basically regioselectivity is the preferential reactivity of one site over the other of other site of the same functional group. So let's say here we have, so this is our starting material and we have the olefin. And if you look at the olefin, this is the terminal center and this is the terminal carbon and this is the middle carbon. So if you add the HBr, so this Br negative will be attack on this middle carbon and the proton attack on the terminal carbon. But if you do the same HBr addition in terms of these per acids, so if you just PHC double bond O, so this is the basically this is the peroxide and this is the peroxy linkage. So if you do this reaction in place of this peroxide, so this Br negative will be attacked now here on the terminal carbon and the proton attached on the in between carbon. So this is the reactive difference in presence of the peroxide and in absence of the peroxide of this HBr on the olefin. So this is about the regioselective addition of this HBr on the olefin. Now if you do the hydration of alkene, so this is our starting material. So if you look at here, this is the more substituted carbon and this is less substituted carbon. So if you do the BH3THF addition and then the workup, so where the hydroxy group will go? Hydroxy group will go on this center. But in presence of let's say Hg mercury acetate and then NaBH4, so this hydroxide group will go to the center which is more substituted. So if you look at the reaction mechanism of this hydroboration reaction, you will understand why this hydroxide forms at this center. Then if you look at here another question, so here this is the alkyne and if you add the HgSO4 and H2SO4, that's the acid. This HgSO4 is the oxidizing reagent. So this ketone group sorry, carbon group forms on the middle carbon. But if you do the BH3THF and then the NaOH H2O2 addition, so this carbon group will form on the terminal carbon. So this is how hydration, radioselective hydration of alkynes occurs in the different reagent condition. The another is the Baer-Villiger oxidation reaction. So if you look at the starting material for this Baer-Villiger oxidation reaction, so this carbon addition carbon is the more substituted, this carbon is the less substituted. And if you add the acid and the reaction occurs, Baer-Villiger reaction occurs here. This the oxygen insertion takes place on the site of the more substitution. So we had the two options, either addition occurs from this side which has a less substitution, or the addition occurs on the site where there is more substitution. In this Baer-Villiger oxidation reaction, this hydroxy insertion takes place on the site where the addition carbon has the more substitution. So this is also the one of the radioselective example of radioselective reaction. And we all know the Birch reduction reaction. This is also one of the example of the radioselective reaction. So here, so this is the electron donating group. And here there is electron withdrawing group in this starting material. And if you look at closely, under the same reagent condition, we get the two different type of product. So this is because the radioselective reaction occurs in terms of these two different substituent on the same type of benzene core. So whenever electron donating group is there, so you have to keep in mind. So this double bond will come addition to that group, and other group will be obviously the on opposite side. And when there is electron withdrawing group, so like this one, acid, so it will always will be like this parallel. So you can keep in mind that pictorially you can remember this one. So these two different type of product we get. So this is on the electron withdrawing group and electron donating group. So this shortcut you can keep in mind. You can it will be easy for you to solve such type of questions very quickly. So these are the radioselective reactions, examples of radioselective reaction. Okay, so then I will discuss some of the name reactions which are involved in the your assignment questions. So the first name reaction is the Fevsky rearrangement. So does anyone have any doubt whatever we have discussed today up to uh, this previous slide? If you have any doubt, please let me know. So we'll discuss that one right now, and also we'll move to the next questions, next slides then. Okay, so this is the one name reaction, which is the Fevsky rearrangement reaction. So basically, if you have such the base or the nucleophile, I'll write here the nucleophile. This is what we get in this reaction. This Nu negative is the nucleophile. So this is the Fevsky rearrangement. So how the mechanism of this reaction works. So the base attracts the proton. Obviously, we know the proton adjacent to the carbonyl group is acidic. So once this proton is attracted, then anion form on the center. So which will be obviously in conjugation with this oxygen. When it comes back, it will directly attack on the adjacent and this chlorine get eliminated. We get such intermediate step, and Then another second nucleophile attack on this carbon center, and this rings, the three-member ring gets open. So like this. So this three-member rings gets open, and from the anion, the negative charge will get here, and from the solvent, it acts like the proton and get the this type of product. So this is basically the Fevsky rearrangement reaction. Another reaction is the phenol rearrangement reaction, and how this reaction occurs. So let's say if you have such substrate, I will just write a simple form in the simple form. So let's say we have this such type of substrate. So this R can be anything on the center. This R, I will just write down the R for simplicity, or I will just leave the methyl, just simple. And in presence of acid, what happens? One of the hydroxy group gets protonated, this OH2 plus, and since this is the uh, tertiary hydroxy group, upon elimination of this entire OH3 plus, what happens? We get the, so here there is OH, this cation, carbocation here, and from this carbocation, so this hydroxy group has the lone pair of electron which push here in, and then this entire methyl group migrate to here, and what we get? We get here on the center now the carbonyl, and on the center there is 3-methyl group. So this is what we get as a product in this pinnacle rearrangement. So this one hydroxy group get eliminated, and this get forms in the forms ketone, and one methyl group migrate here. So this is what basic we get in this reaction. So if you just generalize this reaction, what will be the so this is the starting, and what will be the product in terms of the H plus? The product is like this. So this is the pinnacle rearrangement reaction. It occurs in presence of the acid. Then there is the another reaction is the aldol condensation reaction, and basically this is the aldol condensation reactions are the two different types. Either it is base catalyzed aldol condensation or the acid catalyzed aldol condensation reaction. Generally, both have the similar sort of reaction mechanism. Only the reagents, the uh, in the base catalyzer aldol condensation, the base is used. So this base abstract the proton. So base abstract the proton, which is adjacent to the carbonyl center. So once this proton is abstracted, it forms the enolate, and this enolate attacks on the another molecule on the carbonyl center, and we get the formation of this enolate. And this, sorry, this O negative, which abstract the proton from the solvent, and we get the alpha beta, sorry, beta hydroxy ketones or the aldehyde. So this H can be either uh, this can also be any alkene or alkyl chain or the phenyl ring. So not necessarily it will be hydrogen. And okay, if you get the beta hydroxy ketone or aldehyde, then upon heating, what happens? There is this proton more reactive. So this proton can further abstracted because in the reaction we have the base. So in the base catalyzed reaction we have the base right here. So this proton again is ready for abstraction. So this proton is getting abstracted. So it will form the negative charge on the center, and then this OH get eliminated. So basically we get the, and this again the R group, whatever here another R. So this is what we get, alpha beta unsaturated carbonyl compound. Okay, here there is the mechanism given. So this is the aldol condensation reaction. And in acid catalyze, similar occur. What happen? So in acid catalyze, this acid protonate the carbonyl center, and now from the water, this reaction only works at the aqueous solvent. So water abstract this proton now, because this carbon center will be become more electropositive, because this OH is now protonated. So this proton is getting abstracted by the solvent, and it forms such type of enolate, and which further attack on the another molecule, and the reaction goes further in the similar manner. So you can also note down this acyl catalyzed aldol condensation as well as the base catalyzed aldol condensation reaction. Another reaction is the Luce reduction. So this is the selective organic reduction of the alpha beta unsaturated saturated ketones to the allylic alcohol. So let's say we have the alpha beta unsaturated ketone. So this ketone, and this is the double bond. So this is alpha beta unsaturated ketone, and in terms of the NaBH4, and also the important thing is the CeCl3. So this is the important reagent. So in terms of this, it will form this alpha beta unsaturated alcohol, and this reduction reaction is called as a Luce reduction. You can have a look at this reaction mechanism. So then another reaction is the hydroboration reaction. So in this hydroboration reaction, so if you have the asymmetrical olefin, that is the one carbon is the different than the other of these olefin part. So this BH3 addition occurs in this manner. So this BH2 will be added on the terminal part, and the hydrogen attached on the middle part. And in place of the H2O2 or the base, so it gives the alcohol on the terminal centers. Okay, so till now, does anyone have any doubt? So I believe you can able to solve most of the questions given in the assignment. And do I really need to discuss any assignment question? If you want to discuss many the question from the assignment, you can ask me right now.
Excuse me, sir. Hello.
Yes, please. Yes, please.
Sir, can we get your what you discussed today? Can we have its PDF in your
Uh, uh,
class?
these slides, yeah, I generally upload on the. Okay, you don't have the link for that drive. So okay, I will send add the link for the drive. So whatever the session that I discuss, I generally upload all this 50 on the same drive. So I will share the link for that drive as well. So just a moment.
Okay, that will help. Actually, I want to. I have some eye problem, so I feel problem. I want to print out the papers and then I can. Mm, little
No
bit.
issue. Yeah, I will share the link for that drive. So
If you
just
are, actually,
add in the.
I could not attend your last class. So if I can get that also, all the
Yeah,
session which we
all
discussed.
session. Yeah, that drive contain all the PPT slides. So just a moment, I'm just adding the link for that one.
Okay, sir, sir. That will help. Thank you, sir.
I have added it in the chat box. Can you have a look? Can you check whether you can able to download the PPTs from that one? And also I have added some reference book in the same folder. So also have a look from that one also. Are you all got the link for the drive from the chat box? So I have shared the two links. One is for the uh, one contain the PPTs, whatever I discuss in the this type of sessions every week, and the earlier link was for the reference books. Okay, if you got the link, then we'll move to the our next part of the session. So whatever discussed today is all about the supporting information for our course on the retrosynthesis. So I hope you got clear most of the points from the this chemoselectivity and the regeoselectivity, and also whatever the name reaction and the question that I have discussed, you should able to solve the assignment questions as well. I will move to the now the actual problems on our course on the retrosynthetic analysis. Okay, so this is the first example for the today's session on the retrosynthesis. So let's say this is our target molecule. So this is the target molecule which contain, you can see this alkyl chain with this carbonyl and the phenyl. So from the starting material, we have to break down this molecule into the simple possible molecule. So how the retrosynthesis of this molecule has been done. So upon functional group inversion, so this carbonyl can be alcohol. So this is basically functional group inversion. So this can be achieved from the hydroxy group or the alcohol group, right? Then the next step was the disconnection, carbon-carbon disconnection. So this can be disconnect from this position, and we can get these two type of synthon. So this is the donor synthon, which has the negative part, and this is the acceptor synthon, right? And if you look at the synthetic equivalent for these two parts, so for this carbon, say this cation or the acceptor synthon, the synthetic equivalent is the this H C double bond OPH, that is the benzaldehyde, is the synthetic equivalent. And if you look at this one, so this benzaldehyde is the quite commercial molecule and quite simple molecule. So this is our one of the starting material now. So this is done. Now the another part is this is the negative charge donor synthon can be achieved from this Grignard reagent, that is MgX or MgBr we can say. So this is the synthetic equivalent for this negatively charged syntone, and this how we can achieve this Grignard reagent. We can achieve this from the either from the alkyl halide or alkyl bromide, anything alkyl iodide or bromide. So this is the starting material alkyl bromide. And if you do the synthesis of this molecule, so what we can do now, we have the propyl magnesium, propyl bromide. So this is the first one was the retrosynthetic analysis, and now this is the actual synthesis that we are going to do in the lab. So this is the propyl bromide. So if you add the magnesium in the diethyl ether, and particularly I have to highlight here, this should be the dry, that is unhydrated, without any moisture. So when you do this reaction, we get this Grignard reagent. And so this is the Grignard reagent, right? Then we can do the addition of this Grignard reagent on this benzaldehyde. So what we can get, we get this alcohol, and upon oxidation. So if you just add the pyridium chlorochromate or any oxidizing reagent, so it will selectively, it will do the oxidation. So this is basically we get our the target molecule. So this is how we have to do the uh, retrosynthetic analysis and the synthesis of this our target molecule that whatever we have given. So this is one simple example, and I hope from this example, you can now able to understand how this retrosynthesis we can do for um, target molecule that we have given. So here, whatever we can, what concept we can understand now. So this is the first one was the functional group inversion. So this is the FGI, functional group inversion. Then this is the disconnection, synthon. This is the again synthon, synthetic equivalent, and again the our regular synthesis also different conditions like Grignard reagent preparation followed by the Grignard addition and the oxidation of the alcohol. So this is what we can do the retrosynthesis of such simple molecules. So if I just took the another example, we'll take the simple questions and then we move to the difficult questions later part of this course. So this is the another molecule. So this is our target molecule, and what we can do, we have to prepare this molecule. So how we can achieve this molecule? So we can do the similar manner as earlier question. So this is very similar example or identical example. Here on the A part, we did the disconnection and we got the donor synthon and the which is obviously achieved from this methyl magnesium bromide and the acceptor synthon which can be achieved from uh, this aldehyde. So this is what the simple retrosynthesis of this molecule. The one other possibility is so we can also do the disconnection on this B part. So here the functional group inversion. So this B part can be disconnected. Basically, this can be sorry the functional group inversion. So this alcohol can be prepared from this aldehyde by reduction. So this is functional group inversion reaction. And once we have this carbonyl compound, then we can add on this one. So this part by doing this from this CH3CH2 positive or the CH3CH2 bromide, and this is the another part of this upon the disconnection on this position on this B disconnection. So this is what the starting material. So basically, if you try to do the synthesis of from this B part, so how we can do? We have this acetone, and we add the base plus this iodide. So base abstract the proton from this position, right? So this proton can be abstracted. So it will form the negative charge. So how it will be? It will be C double bond O negative, sorry C negative, and this negative can attack this position. Iodide can eliminate it, and we get the. And then if we do the reduction of this carbonyl, so that will be our our product, right? Or the target molecule. And if you go by the route A, the route A is the more feasible route. If you do go by route A, how it will be? It will be only directly the grignal addition on this aldehyde. So this grignal we can prepare from the propyl bromide and the magnesium. It will be methyl magnesium bromide. Then we do addition of this methyl magnesium bromide on this aldehyde. We can get this intermediate, and upon workup we get our target molecule. So this is the one. So among these two routes, so which route will be the more synthetically feasible? So this route A is more synthetically feasible. Why? Because if you look at the, I will take it on the new slide. Whatever the route A, what I discuss, the route A, what I have discussed was like this. We add the base. Base will form the anion at this position, neutral charge. And then if we add this iodide, so this negatively charged attacks on this position, this iodide get eliminated, and we get the this product. And upon reduction we get this product. So by synthetically, sorry, by visibly it looks very similar, sorry, simple reactions, like just addition of the base on the base will form the anion, and upon formation of this anion, so it will if you just add the ethyl iodide, so it will give the ketone compound, and then upon reduction it will give the alcohol, that is our target molecule. But if you look at the complexity of this reaction, the first step, that is the selectively one equivalent alkylation, is difficult. Why? Because we have now, this is the one, two, three protons, and how many products will be possible from this one? There are heaps of products, side products are possible. That is by mono substitution, by di substitution, by di substitution at the two different from the two different side, for tri tetra substitution. So we get the lot of side product in this reaction. So therefore, if you look at the route A, which is shown here, it doesn't have such issue. So we just need to prepare the grignal, and upon addition of this grignal to this benzaldehyde, we get the target molecule. So therefore, uh, there will be some cases more than one synthetic routes are possible. That time we need to also look at the practically whether it is feasible or not. So that also we need to keep in mind. So any doubt in this one? In this question, there are more than one routes possible. So based on the two different paths, we have to look at the how practically we can perform this reaction. That's what we have to. Now I will take the another example. Okay, so this is our target molecule. So this is the target molecule. Now, if you do the retrosynthesis of this target molecule, how we can do? So this we can do the disconnection here, because we know this alpha carbon to the carbonyl will be the electronegative, and this is the electropositive center. So we can do the disconnection on this center, and we get this donor synthon. And what we can get, this is the first thing, we get this donor synthon, and we get the another acceptor synthon. So this is what we get the first, right? So how this can be achieved? This can be achieved from the simple acetone molecule, right? Or from the enolate, or from the acetone, right? So these are basically the synthetic equivalent for this donor synthon. Now, what the second part we get from this one? We get the second part, that is the cation, which has the hydrogen hydroxy group. So this is positive, and we can achieve this from this synthetic equivalent, that is the epoxide. So if you do the synthesis of this linear synthesis of this molecule, so how it will be? If you just add the base, so it will form the enolate, and upon addition of this enolate on this epoxide, it will selectively do the addition on this center terminal, because the terminal one is less sterically crowded. So they selectively do the nucleophilic addition on this terminal terminal center, and we get this uh, epoxide opened O negative and anion, and upon workup we get the our target molecule. So this is how we can achieve the synthesis of this target molecule. And similarly, we can use this approach for synthesis of either this type of molecule, whichever we have discussed right now, or if you have such uh, alcohol, we can do the addition of this alcohol on this epoxide in the same manner. So this type of retrosynthetic analysis we can achieve use for, this is our example that we have discussed. This type of molecule also will be do the similar type of disconnection and similar retrosynthetic analysis we can use also for this type of amines. If you have the secondary amine, we can do the epoxide addition in the similar manner. So this different type of target molecule we can achieve by this type of retrosynthetic analysis. So similar route will be followed from this ring opening of this epoxide. So if you just give some more target molecule and the different type of synthons and then the synthetic equivalent. So if I just add one more slide. So let us say this type of target molecule we have now. So these are the target molecule given, and different type of synthons, possible synthons are given here. So if you have such similar target molecule, the disconnection we can do on this position. So it will be this synthons will be like this C positive. So this can comes from the either formaldehyde or similar sort of starting. If you do the disconnection here, so the synthons possible are C negative, and here there is positive, and obviously this can we have already discussed. This can comes from similar sort of epoxide. Then if you do for the third molecule, if you do the disconnection here, this can come from this positive and this Cn negative, and this positive can achieve from the either from the iodide, and this Cn, this can be nucleophilic cyanide. Another molecule is this one. We can do the disconnection at this point because we know the alpha position of this carbonyl is electron negative. So this negative synthon, donor synthon will be like this, and acceptor synthon will be like this. And this can be either achieved from this type of center, and this can be achieved from like this. We can abstract the proton from this one, and then this can do the addition on this point, carbonyl center. So this is what for today's session. So if you have any doubt, so please let me know. Does anyone have any doubt on the question given in the assignment? I think assignment questions are quite easy, so you should be able to solve all the questions. The first question basically based on the aldol condensation reaction that we have already discussed. Base catalyzed aldol condensation reaction. Second question is on the Pevsky rearrangement reaction. The third question is based on the this one. It's simple, I think. We can do the reduction and we can stop the reduction of the alkyne at the alkene stage by using these H2 Lindlar catalyst, and then we do the hydroboration reaction and the peroxide addition. So the this will be the option A will be the correct for the third question. And I think remaining all questions are much easy. The Grignal Grignal reaction is given, so that should be easy. The question 5 is on the beer vinegar rearrangement reaction, and I don't think I need to discuss that one. The sixth question is on the selective epoxidation of the olefin, and particularly here example given is the alpha beta unsaturated olefin. So you know which reagent will be you are going to use for this epoxidation reaction. The seventh question is somewhat complicated, but it is on the aldol condensation reaction. So you need to spend a lot of time to get the answer for that one, but it's doable. The eighth question is on the selective reduction of the alpha beta unsaturated carbonyl compound. Eighth question is about the B2H6 addition on the olefin and the further oxidation. And sorry, this was the ninth question. And the 10th question is on the pinacol rearrangement reaction. So I have solved most of the similar concept in this today's session. So you should be able to solve all the assignment question. Okay, does anyone have any doubt? We can stop here for today if you don't have any doubt. So whatever discussed today, so I will upload this PPT in the folder so you can refer this PPT. Okay, thank you for joining. So we'll see you on the next Tuesday. So if you don't have any doubt, you can leave now.